Okay. Testing.
Yo.
Okay. All right. If you have no problem, we need to get your all your solution feedback, because I need to keep it so that just in case that we have we call the university accreditation committee. They come to review our university's the whole program, and sometimes they will request us to show them what kind of the exam problem I give to the students. Yeah. So anyway, but the most important thing is don't worry about your exam too much, because you won't occupy too much percentage in your overall score. In my past experience, that each exam maximum percentage will be only about 20% each. All right. So your homework will be more important than your exam. Exam is at least give you a chance to show how much you understand the lecture. That's all. Because last week I had some infections, so I couldn't come, and I'm not fully recovered yet. Sometimes please allow me to sit down. Okay. Now today, I think we talked about this 2 weeks ago, a little bit. Let me review just a little bit in the quick, so that you still remember what I did, and I also myself I remember what I did. And we already learned we call virtual passive control, the output feedback technique. And here we talk about the state feedback. The state feedback we do have a state observer X hat called estimated state called X hat, and that X hat means some of the states we do not measure. For example, like this case, we measure Y, and this Y can be velocity only, can be displacement only, can be acceleration only, like that. And so then you need your we call the observer to estimate the other state you don't measure. And again, the U here, if you look at U here, the input here, U here is equal to the function f times, we call it gain, control gain times x hat. So this x hat is not real x, it's the estimated from this estimator, and then, so your U really is constant f times x hat. Now, what kind of f we will use? That's in this class. We'll show you several different methods to do that. Now, one of the methods we call Paul placement. That's what we are going to do in this class. And then the next one will be optimum control. So basically, I will introduce these two different techniques, one called Paul placement technique, one called optimal control technique, to compute the f, that f here. What kind of gain we are going to do. Okay, and I keep saying that the eigenvalues of a system is the one to determine the system is stable or not. Even open loop or closed loop, that's all determined by the eigenvalues. So your eigenvalue are the value determine your system stability, your performance as well. So that's what we need to talk about this time, right? So here we say design a full state feedback controller for a controllable system. Now, what do we mean controllable system? I don't have chance to discuss about the controllable system. Now, in this lecture, we all assume the system is controllable. We just assume that, all right? And we'll use called North-Bayes technique to determine the controller gain. So the controller gain will be determined by the North-Bayes technique, so that your closed-loop eigenvalue will be your desired eigenvalues. Okay, so I already introduced some of the basic concept about here, and here we have U equal to F1W plus F2W dot. We have F1 is a constant, F2 is a constant. By the way, suppose U should be F1 the W hat plus F2 W dot hat. So supposed to be estimate state. Now here, I assume that the W and W dot, we do have a measurement for W and W dot. Here I just assume that, okay? So I assume that I have W measurement, I also have W dot measurement. So I can have F1 times W plus F2 W dot. As a matter of fact, I may not have a time to prove to you that under this assumption I have W and W dot. If I don't have W and W dot, if I replace it by W hat and W dot hat, as a matter of fact, you get the same results. But there's a mathematical proof can be done to say that. All right. So here it allows me to assume that I have W and W dot, or I assume that my W hat and W dot hat are identical to the true W and W dot. Understand now? Because I proved to you already, right? A few weeks ago, giving any initial conditions, only two or three steps, all your estimate state converts to true state. Did you recall that? Yeah, so that's true, right? So, as a matter of fact, if you do a good job in your observer, your hat, your estimated, supposed to be very close to the true state, if not identical to the true state. It's supposed to be very close to the true state. All right, from here on the closed-loop system, if I sub this U into this original system, then I got this closed-loop system. This is what we call open-loop system. W double dot plus W equal to U, that's an open loop, because I have U there. If I give you U equal to F1W plus F2W dot, then I sub this U into this open loop and move on the right-hand side W and W dot to the left-hand side, and this I call the closed loop system. Any questions? So open loop system here and closed loop system here, the eigenvalues are different. The open loop system without U, this eigenvalue is plus minus I. The eigenvalue for this closed loop system will depend on your F1 and F2. So if let W equal to C E lambda T, then we solve this closed loop system, then I get these equations for you to solve the eigenvalue lambda. Assume that if you give them F1 and F2. Now, on the other hand, if I say I know what kind of closed loop eigenvalue I need, assume that this is the eigenvalue, the closed loop eigenvalue I desire. Here, if I say I want to desire these eigenvalues, minus 0.5 plus 0.886i, minus 2, lambda 2 equal to minus 0.5 minus 0.886i, then that's my closed loop eigenvalue. Then you may ask, how do I know this kind of eigenvalue I need? Right. Do you have any question like that? Why I know this is the eigenvalue I need? How do I know? How do I know this is the eigenvalue I want? First of all, if you want a closed loop system to be stable, then your real part has to be minus. Agree? Has to be minus. Right? Because E lambda t minus 0.5 plus 0.88i6i, then E minus lambda t, then I know that when t grow, this W will be what? Will decay. Agree? Right. Let's look at the this closed loop eigenvalue. W equal to W equal to C E lambda t equal to C E lambda 1 is minus 0.5 plus 0.886 I then t. Then I have C1 plus C2 E minus 0.5 plus minus 0.886 I and t. Now, if you look at this one here, C1, then E, I can write it come like this, E minus 0.5 t, then parentheses C1 E 0.886 I t plus C2 E minus 0.886 I t. Right? Am I right? In terms like that. And this one, when t grow, this is decay. When t grow to infinity and infinite, then this becomes zero. All right. So this is why I choose number 1 equal to minus 0.5, because I need this negative here to make system to be stable. If I choose this positive, then what happens? The closed system will be grow. Then why? And then I say, then you might ask, say why do I choose minus 0.5? Why not minus 0.6? Why not minus 0.7, 0.9? That depends on your performance. So what kind of performance you want to have? you have to keep in your mind. This minus 0.5 chosen here just as example. And when you know what kind of performance you want, then you have to determine what kind of closed loop eigenvalue you want to have. And plus, this complex and conjugate has to be all come together. You cannot have has to all come together. So you have complex and conjugate. All right. Any question about this now? Okay. Now let us look at back here. So that's why I choose the lambda 1 and lambda 2. Here is I have a point of 0.5 minus 0.5 minus 0.5 plus 0.886i minus 0.886i. They come with a pair. Has to come with a pair. You cannot come alone, right? Because your system is always real. The system cannot. This W has to be real. This W cannot be complex. Eigenvalue can be complex, but your final results W cannot be complex. So, if I have this closed loop desired closed loop eigenvalue, then I can determine compared to these equations. I know my control gain F1. This F1 equal to 0. This F2 equal to minus 1. So F2 equal to minus 1. So my final input, the control force will be U equal to minus W dot. It happened to be like that. F1 not necessarily always equal to 0. No. Any question about this? Simple example.
F1 and F2, how you choose it? Or?
For example, F2 here minus F2 equal to minus F2 equal to 1. 1 minus F2 1. 1 minus F1 equal to 1. Compare these two polynomials, then you will be able to determine your F1 and F2, right? Is that your question? Okay. This is the simplest way for pole placement technique. We place the pole, the open loop pole, from plus or minus I to this lambda 1 and lambda 2. When we give this feedback, when we have this feedback, and this feedback will be able to allow us to change my open loop eigenvalue to the closed loop eigenvalue, which is we call the desired closed loop eigenvalues. Any questions? This is the simplest way to do it. That means I want to change my system so that I have damping. For example, originally, this system has no damping. This system, no damping. But when we give this U, then your closed loop system now has a damping. This comes from 0.5, minus 0.5. Okay. So that means here. So the slide last page will be, if I have W dot measurement, then I can just U equal to minus W dot, because F1 equal to 0, F2 equal to minus 1. and I use this as my control force feedback, then that's we call the pole placement technique. I did not have the a state estimator here. I assume my state estimator give me the estimate state W dot exactly. Okay? That's all. All right, let us look at the basic concept. Then I show you the continuous time feedback. The discrete time model should be the same thing. This is my discrete time model. This is my open loop. My open loop, A equal to cosine delta t, sine delta t, minus sine delta t, cosine delta t. And B is 1 minus cosine delta t, sine delta t. You can choose your sample interval you want. Control force, the same thing. U equal to Fx equal to F1, F2, then F1 times Wk plus F2 times W dot K. All right, then my closed loop system becomes this. A plus BF, A plus B times this F, then this is my closed loop system state matrix. Any question about this? B is here. F is F1, F2. B times F means this 1 minus cosine delta t, sine delta t times F is F1, F2. And this has become my closed loop state matrix. This is my open loop state matrix. A here, cosine delta t, sine delta t, minus sine delta t, cosine delta t. This is my open loop state matrix. This is my closed loop state matrix. And this closed loop state matrix has F1 and F2. That to be determined. Any questions? Maybe I jumped too quick. A is here. B is here. Times F. F is F1 and F2. Any question about this? No? Yes? Follow me? No? Okay. Let me write down here. All right. A, my open loop, A equal to cosine delta t, and sine delta t minus sine delta t. That's my open loop state matrix. This is what I call open loop. This open loop state matrix. All right. Now we have xk plus 1 equal to a sk plus b uk. All right. This A xk plus B F U, this UK equal to this UK is the Fx. So BFXK. So that means A plus BFXK. So that is my closed loop state matrix. Any questions? U, my control force equal to Fx, not Fx. So I sub UFXK. So that means A plus BFXK. All right. So you sub B there. You sub B. This B is 1, and well, B equal to 1 minus cosine theta t cosine theta t. F equal to here F1 F2. So B times F, you know how to do matrix, right? So B times F plus A, that's that one, A plus BF. So that is, I call the closed loop state matrix. This is discrete time model. Any questions? You just sub A there, put A, this one there, B, this one there, F, that one there, and you add together. That's mine, A plus BF there. Any questions? You think that clear enough? Because I already replaced U to be my Fx. So this become my closed loop state matrix. Any problem? No? Okay. That's clear enough, right? All right. Let's go back to the notes, to the lecture notes. Okay. Now, I have a closed loop system state matrix A plus BF. Now, I have F1 and F2 I need to determine. What kind of F1 and F2 I need? It depends on what kind of eigenvalues I want to have. So special case, that's the delta t equal to pi over 2. Assume like that. My closed loop system A plus BF become F1, F2 plus 1, F1 minus 1, F2. That's my closed loop state matrix. Become very simple when delta t equal to pi over 2. All right. Now, what is the closed loop eigenvalue I have? A plus BF minus lambda or I. If I want to solve eigenvalue problem of this A plus BF, then what I need to do is to solve the determinant of A plus BF minus lambda I. Right? Eigenvalue. I want to solve eigenvalue of this matrix. How can I solve eigenvalue of this matrix? Just A plus BF, that matrix, minus lambda I, take determinant equal to 0, right? Then if you sub like that, my eigenvalue problem becomes this. Lambda square minus F1 plus F2 lambda plus 1 minus F1 plus F2 equal to 0. This is my eigenvalue problem. All right? For a 2 by 2 matrix, you can do that. For 3 by 3, well, it's getting more difficult. For 4 by 4, you're out of luck. For 10 by 10, well, you can solve for lifetime. That's why later on I will show you a null space technique to solve it. You don't really solve this for 10 by 10 or 100 by 100 matrix. No. More than 2 by 2, you don't want to do that anymore. All right, but for 2 by 2, this is show you the concept. Then I say, well, this is the eigenvalue I want to have. That's the eigenvalue. All right. And I say, okay, I want to desire close to eigenvalue. The same questions you might ask. Why I have a half year, 1 plus I, half year 1 minus I? Why? I already taught you also in your midterm example, in your midterm problem. But just discrete time model, the eigenvalue must be within the unit circle so that the discrete time model system is stable. Understand? This is why I have to choose. If I want this closed loop system to become stable, my closed loop eigenvalue, desired closed loop eigenvalue, their amplitude must be what? That's an all equal to 1. You know why? Huh?
I don't know why.
You don't know why? Okay. Let us look at the easy to do. All right. Let us look at the continuous time model first. This is my eigenvalue. This is my eigenvalue real part. The eigenvalue imaginary part. The continuous time model, if they want to be stable, the real part of eigenvalue has to be what? Negative. So this is a stable. This is a stable region. If your eigenvalue, real part eigenvalue is positive, they're unstable. Agree? Unstable. All right. Now, when we transform this through a exponential lambda r plus I lambda I, discrete time. What is discrete time? If this is continuous time, the discrete time A is E AC delta T equal to A. That's my discrete time, right? So the eigenvalue of that is times delta T. If I, for all the eigenvalue of this, if I do the discrete time times delta T, and this is my eigenvalue of AC, that's real part, imaginary part. Agree? Discrete time, I have to take exponential. Right? Okay? All right, now. This stable region, after I take exponential of this stable region, what happens? All this is negative. The I doesn't do any good. Doesn't do anything. Because that's I is sine cosine. So all the stable region, let me put the phone here. E negative lambda r times delta t, what does that mean? Stable? I know it's stable. If E take a negative value, can be then larger than 1? No. Right? So that means all the stable region we map inside the unit circle. All the unstable region outside the unit circle. I understand? Right? Exponential, if this is positive value, has to be larger than 1, right? if this negative has to be less than 1, right? So that's why I want to choose that by lambda 1, lambda 2. The amplitude must be less than 1. The stable region will map through this exponential function will map inside unit circle. Unstable region map outside of unit circle. When lambda r equal to 0, that's in on the unit circle. Right? Although my unit circle is not really good shape, but obviously I'm not a good artist there. So. Now you understand now? Okay, good. Yeah, it makes sense, right? So also good. Now, can I go further? Okay, that's turn back to my next note. All right, so if I want to be stable for my cross-two eigenvalues, then my lambda 1 and lambda 2, if you look carefully here, lambda 1 I choose to be half 1 plus I. You know that the amplitude of lambda 1 is less than 1. So this is stable eigenvalue. Again, you also have to choose the complex conjugate. Doesn't matter if discrete time or continuous time, the eigenvalue always come a pair. Complex and its complex conjugate. All right, now, I want to form the same polynomial like this. If I have a cross-two eigenvalue, desired cross-two eigenvalue like that, then my polynomial has to be equal to lambda squared plus lambda plus half equal to 0. And I compare these two polynomials, and I will be able to determine my gain. Right? Oh, oops. Then I will determine my gain. F1 plus F2 has to equal to minus 1. 1 minus F2, F1 plus F2 will be equal to half. And I have two equations to solve two unknown. So my F1 equal to 1 over 4, F2 equal to 3 over 4. That's my gain, F1 and F2. So if I know my desired cross eigenvalues, then I will be able to determine my control gain to be like that. Any questions? This is a basic concept. So if I know the cross eigenvalue, I will be able to compute my control gain to give me the cross-two eigenvalue I desire. Of course, to choose cross-two eigenvalues, this is what I just want them to choose. You don't do that. When you really try to design a controller, you out to have an objective. What kind of performance? What kind of decay? How fast decay I want to be? Then I can choose certain eigenvalue I want so that I can achieve my performance. Understand now? At this moment, I did not talk about the eigenvector yet. Nothing. For this case, you have no choice about your eigenvectors, your cross eigenvectors. You have only freedom to choose your cross eigenvalues. You don't have any freedom to choose your eigenvectors. So called the cross eigenvectors. So I did not talk about that yet. All right, let us take a minute, 10 minutes off.好，没关系，好，谢谢。
然后就是想要